Welcome back. This week, we're going to cover more on inferential statistics and a little more in depth, as we will learn how to statistically test hypotheses. We've previously covered descriptive statistics in great detail. Remember the three types of averages, mean, median, and mode, as well as standard deviation and standard error of the mean. Now we will learn how to calculate some inferential statistics, starting with simple hypothesis testing. As you know, a hypothesis is a statement about a population where this statement typically is represented by some specific numerical value. In inferential statistics, we test statistical hypotheses which are different from experimental hypotheses. To understand what this means, assume that you do an experiment to test whether nitrogen promotes plant growth. This is an experimental hypothesis because it tells you something about the biology of plant growth. To test the hypothesis, you grow 10 bean plants in dirt with added nitrogen and 10 bean plants in dirt without added nitrogen. You find out that the mean of these two samples are 13.2 centimeters and 11.9 centimeters, respectively. Does this result indicate that there is a difference between the two populations and that nitrogen might promote plant growth? Or is the difference in the two means merely due to chance? A statistical test is required to discriminate between these two possibilities. In testing a hypothesis, we use a method where we gather data in an effort to gather evidence about the hypothesis, and there are certain steps one must follow. First, we must set up two competing hypotheses. Each hypothesis test includes two hypotheses about the population. One is called the null hypothesis, notated as H sub O, or H naught, which is a statement of a particular parameter value. This hypothesis is assumed to be true until there is evidence to suggest otherwise. The second hypothesis is called the alternative or research hypothesis, and it is notated as H sub little a, where the a is substituted for a different number in some cases. The alternative hypothesis is a statement of a range of alternative values in which the parameter may fall. One must also check that any assumptions or conditions needed to run the test of choice have been satisfied. Examples of these include normality of the data, whether they're distributed normally, independence of the values, and number of success and failure outcomes. We'll come back to these concepts later. The second thing is that we must set some level of significance, called alpha. As we learned last week, this value is used as a probability cutoff for making decisions about the null hypothesis. Remember, this alpha value represents the probability we are willing to place on our test for making an incorrect decision in regards to rejecting the null hypothesis. The most common alpha value is 0.05 or 5%. Other popular choices are 0.01 or 1% and 0.1 or 10%. Next, we must calculate a test statistic. We need to gather sample data and calculate a test statistic where the sample statistic is compared to the parameter value. The test statistic is calculated under the assumption that the null hypothesis is true and incorporates a measure of standard error and assumptions or conditions related to the sampling distribution. Again, such assumptions could be normality of data, independence, and number of success and failure outcomes. Next, we calculate a probability value, or a p-value, which we learned a lot about in the last lecture. We can also find what's called a rejection region, and we'll talk about that in just a second. A p-value is found by using the test statistic to calculate the probability of the sample data producing such a test statistic, or one more extreme. The rejection region is found by using alpha to find a critical value. The The rejection region is the area that is more extreme than the critical value. Again, we'll talk about this in more depth later. Next, we make a test decision about the null hypothesis. In this step, we decide to either reject the null hypothesis or decide to fail to reject the null hypothesis. Notice, and this is important, that we do not make a decision where we will accept the null hypothesis. There are only two options. You can reject the null hypothesis, or you can fail to reject the null hypothesis. After you've made a decision about the null hypothesis, you state an overall conclusion. Once we have found the p-value, or rejection region, and made a statistical decision about the null hypothesis, either reject or fail to reject, we make this conclusion. Following this decision, we want to summarize our results into an overall conclusion for our test. We will continue our discussion by considering two specific hypothesis tests, a test of one proportion and a test of one mean. We will provide the general setup of the hypothesis and the test statistic for both tests. From there, we will branch off into specific discussions on each of these tests. In order to make judgment about the value of a parameter, the problem can be set up as a hypothesis testing problem. Statistical tests evaluate statistical hypotheses. The statistical null hypothesis, symbolized by H0, is a statement that you want to test. In this case, if you grow 10 plants with nitrogen and 10 without, the null hypothesis is that there is no difference in the mean heights of the two groups, and any observed difference between the two groups would have occurred purely by chance. The alternative hypothesis to H0 is symbolized by H1 and usually simply states that there is a difference between the populations. The hypothesis that one wants to conclude is generally set as the alternative hypothesis, or also called the research hypothesis. The statistical null and alternative hypotheses are statements about the data that should follow from the experimental hypothesis. In your research, you are usually interested in testing some sort of hypothesis, like nitrogen promotes plant growth. So you try to confirm your working hypothesis, again also known as the alternative hypothesis, which is the alternative to the null hypothesis. The alternative hypotheses can take one of three forms. The first of these is that it is not equal to a certain value. This is referred to as a two-sided test, meaning it can fall on either side of the value. The second is that the population parameter is less than a certain value, referred to as a left-tailed test, or it falls below or to the left of the value. The third is that the population parameter is greater than a certain value, which is a right-tailed test. Again, it could be above or to the right side of the certain value. For all three of these potential alternative hypotheses, the null hypothesis is the population parameter is equal to that certain value. Using the previous plant example, the alternative hypothesis or working hypothesis, adding nitrogen to plant soil increases plant growth. Confirming the alternative hypothesis is not done directly. Instead, confirming the alternative hypothesis is done by testing the null hypothesis. The alternative hypothesis indicates that some sort of a relationship exists between variables. The null hypothesis indicates no relationship between the same variables. In this example, nitrogen does not promote plant growth. The alternative hypothesis is stated in positive terms such that there will be a difference between groups or that the independent variable will have a significant effect on the dependent variable. Since hypothesis tests are about a parameter value, the hypotheses use parameter notation, a little p for the proportion or mu for mean in their arrangement. For tests of a mean, we would choose the appropriate alternative based on our research question. Here are all of the possible alternative hypotheses from which we would select only one of these based on the research question. Again, the population parameter is not equal to a certain value. This is a two-tailed test, and it looks like this, where the value would lie on either side of your population parameter. Two-tailed test. The population parameter is less than a certain value. This is a left-tailed test. It looks like this. So the value would fall on the left side, or less than the population parameter. And in the third potential alternative hypothesis, the population parameter is greater than a certain value, or a right-tailed test, which looks like this, where the value would fall to the right or greater than the population parameter. To confirm the existence of a significant relationship between variables or a significant difference between groups, you have to confidently reject the null hypothesis. In other words, to say that the difference or significance is not due to chance. If the null hypothesis is accepted, that means that there is no difference between groups or no effect of the independent variable on the dependent variable. The reason for any observed differences would be attributed solely to chance. If we look at an example of testing hypotheses, in this example, the Consumer Test Agency wants to see whether the mean lifetime of a brand of tires is less than 42,000 miles, as the tire manufacturer advertises that the average lifetime is at least 42,000 miles. In this example, we are discussing a mean and therefore set up the hypotheses in terms of mu. So the certain value that we're interested in is 42,000. So the mean of the certain value is set at 42,000. With the Consumer Test Agency wanting to research that the mean lifetime is below 42,000, we would set up the hypotheses as a left-tailed test. And our equations would look like this. Our null hypothesis is that the population mean equals 42,000. Our alternative hypothesis is that the population mean is less than 42,000. This is a left-tailed test. If we look at another example of testing hypotheses with one sample again, the length of a certain lumber from a national home building store is supposed to be 8.5 feet. A builder wants to check whether the shipment of lumber she receives has a mean length different from 8.5 feet. In this example, we are discussing a mean again, and therefore we set up the hypotheses in terms of mu once again. Here, the certain value we're talking about is set at 8.5. With the builder wanting to check if the mean length is different from 8.5, she would set up the hypotheses as a two-tailed test. Okay, and this would look like this in terms of equations. Your null hypothesis is that the mean is equal to your certain value, 8.5, and your alternative hypothesis in this case, in a two-tailed test, is that the population mean does not equal 8.5. Again, this is a two-tailed. One more example. A political news company believes the national approval rating for the current president has fallen below 40%. In this example, we are discussing a proportion, not a mean, and therefore we will set up the hypothesis in terms of p. Here, the p sub naught value or certain value is 0.4, which relates to 40%, right? 0.4 is the proportion. So your p sub naught value is equal to 0.4. And in this case, the hypothesis would be set up as a left-tailed test because here's your null hypothesis that p is equal to 0.4. Your alternative, which has to do with falling below 40%, would be p is less than 0.4. And this is a left-tailed test. The researcher usually decides on the level of significance he or she is willing to fail to reject or reject the null hypothesis. In biology, 0.05 level of significance is most commonly used. This is referred to as P is less than 0.05. A significance level of 0.01 is also commonly used, and this is abbreviated P is less than 0.01. The numbers indicate a probability of 5 in 100 or 1 in 100 respectively. If the likelihood that the difference in measurements that is due to chance is less than 5 in 100 or 1 in 100, then one would decide that the odds are small and hence reject the null hypothesis. There is a significant finding, and it is not merely a result of chance. And so if we look at it on our bell-shaped curve here, so your true value or your mean is going to lie here. If your observed value is here, and this is your observed P or statistical value, these are very unlikely observations, okay, so not due to chance. And this line here is set at your 95% statistical significance threshold, or your P is less than 0.05. And so if you have your values fall in this area, then they're very unlikely observations. And so there's a significant finding. If the difference is likely due to chance more than 5 times in a 100 sample body, or 1 in 100 for 0.01, then one would have no confidence in the findings, therefore the null hypothesis is failed to be rejected, indicating that the difference is in probability, or that the difference is probably due to chance and not due to the independent variable. Testing the null hypothesis is done by performing a suitable inferential statistical test on the data. The image here, as I mentioned, is a visual representation of an example with the commonly used 95% threshold, or p-value of 0.05. In other words, p is less than 0.05, for example, means that only 5% error will be acceptable. Hence, the results must be 95% true. Reporting the results is done by stating that the finding is quote-unquote statistically significant at whatever your p-value is, which is almost always less than 0.05. This means that the finding is not due to chance. In other words, the null hypothesis is rejected and the research hypothesis is quote-unquote accepted. A finding is statistically significant has nothing to do with it being practically important, or in biology, biologically relevant. It simply means that statistics show that chance was not a factor or highly unlikely to be a factor. So again, the probability value for your test statistic, if the probability value or p-value from your test statistic is less than 0.05, you reject your null hypothesis. If your p-value is greater than or equal to 0.05, you fail to reject the null hypothesis. As a recap, before you perform a statistical test on your data, you should determine an acceptable significance level of the null statistical hypothesis. That is, ask yourself, when do I think my results, and thus my test statistic, are so unusual that I no longer think the differences observed in my data are simply due to chance? The significance level is known as alpha. The significance level, again, is the probability of getting a test statistic rare enough that you are comfortable rejecting the null hypothesis. Okay, so if we look at this kind of in a different way of looking at hypothesis testing example, here you have hypotheses being tested. 1, the man is guilty. 2, the man is not guilty. So if a man goes to trial and is tried for the murder of his ex-wife, he is acquitted in the criminal trial by the jury, but convicted in a subsequent civil lawsuit based on the same evidence. Does it make any statistical sense? We can put it in a hypothesis testing framework. The hypotheses being tested are: the man is guilty, the man is not guilty. First, let's set up the null and alternative hypotheses. The null hypothesis is that the man, in this case Mr. Ray, is not guilty. The alternative hypothesis, Mr. Ray is guilty. Here we put the man is not guilty in the null hypothesis because we consider false rejection of a null hypothesis a more serious error than failing to reject the null hypothesis. Remember type 1 and type 2 errors that we talked about last time? A type 1 error is committed if we reject the null hypothesis when it is in fact true. In other words, when the man is not guilty but found guilty. Type 2 error is committed if we accept the null hypothesis when it is actually false. So, in other words, when the man is guilty but found not guilty. Here we have these two type errors denoted as alpha equals the probability of type 1 error and beta as the probability of a type 2 error. What is the relationship between alpha and beta here? The smaller we specify the significance level alpha, remember this, the larger will be the probability, beta, of accepting a false null hypothesis. Significance test is a way of statistically testing a hypothesis by comparing the data to values predicted by the hypotheses that you've set. All significant tests have 5 different elements. These elements include the assumptions, hypotheses, the test statistic, the p-value, and the conclusion. Significance test analyzes the strength of sample evidence against the null hypothesis. The test is conducted to investigate whether the data contradict the null hypothesis, hence suggesting that the alternative hypothesis is true. The alternative hypothesis is judged acceptable if the sample data are inconsistent with the null hypothesis. That is, the alternative hypothesis is supported if the null hypothesis appears to be incorrect. Remember, the hypotheses are formulated before collecting or analyzing the data. This is really important to remember. So how do we decide which test statistic to use? The selection of the most suitable test depends on several factors, mainly the type of data, the distribution of data, and the nature of the research question or hypothesis. Some of the common tests are as follows. For continuous data, the 2 most common tests are the t-test and the what we call analysis of variance, or abbreviated as ANOVA. So here you have, if the y data is continuous, you have the t-test and you have an ANOVA, analysis of variance. So in this case, the dependent variable is the y variable. This variable depends on the independent variable, or the x data in this example. The independent variable is the x variable here. And so we're going to talk about simple t-tests today, looking at one sample test. And by the end of the semester, we will have gone over ANOVAs, chi-square, and simple regression. The 2 tests, the one sample test that we're going to talk about today, and actually we're going to talk mainly about the first one because it's the more complex one, if you will, is the test of one proportion. So the second one is a test of one mean. If the conditions necessary to conduct the hypothesis test are satisfied, then we can use the formulas here to calculate the appropriate test statistic from our sample data. The test of one proportion can be related to a question like, are the majority of students at UAB from the state of Alabama? This is a test of proportions, not of mean, and we'll talk about that question in just a minute. The conditions that must be met for this type of statistic, which is called a z-test or z-statistic, also the test of one proportion. The conditions that have to be met are that n times your p sub naught and or the n times 1 minus p sub naught are at least 5. If so, then the one proportion test statistic can be calculated using this equation right here. Okay, and we'll talk about that in just a second. The test of the one mean. If you want to know whether or not a mean or a population mean is equal to a value, so we talked about that kind of a lot before with our examples of null and alternative hypotheses, then you use a t-test, okay, or a test of one mean. The conditions that have to be met here is that the data satisfies the conditions similar to those used for constructing a t-confidence interval for the mean. These include things like normal distribution, where the sample size with data is not skewed one way or the other. If any of these conditions are satisfied, then we can calculate the following test statistic that looks like this here. So let's assume we take, for the question about whether or not the majority of students at UAB are from the state of Alabama, let's assume we take a random sample of 500 UAB students and find out that 278 of those 500 are from Alabama. Can we conclude that the proportion is larger than 0.5, or being a majority, satisfying a majority? Is 278 divided by 500, which equals 0.556, much bigger than 0.5? What is much bigger? How do you define what is much bigger or bigger? This depends on the standard deviation of P, or the proportion, under the null hypothesis. Let's go back for a second. Here's our question. Okay, are the majority of students at UAB from the state of Alabama? This is an example that we could utilize a test of one proportion, so let's go back to the question. And to answer this, we can set it up as a hypothesis testing problem and use data collected, as we just mentioned, to answer it. This example is about a population proportion, and thus we set up the hypotheses in terms of P. Here, the value of P sub naught, or the certain value we're interested in, is 0.5, since more than 0.5 constitutes a majority. And the question is asking, are the majority of students at UAB from the state of Alabama? The hypotheses set up would be a right-tailed test. Here you have your null hypothesis of P equals 2.5, and your alternative hypothesis is P is greater than 0.5. And so this is a right-tailed test, which would look like this. So again, let's assume we take a random sample of 500 UAB students and find that 278 are from Alabama. Can we conclude that the proportion is larger than 0.5? Is 0.556 much bigger than 0.5? The difference here is our calculated parameter, okay, or proportion here, minus our P sub naught, okay, which is our value or certain value of interest. If we subtract those, the difference is 0.056. Is that much bigger? Is that within the realm of what we consider much bigger? And again, this depends on the standard deviation of the proportion here, okay, under the null hypothesis. So the standard deviation of our proportion, okay, our sample proportion, or parameter proportion, if the null hypothesis is true, okay, when P sub naught equals 0.5, would look like this. Okay, here's our formula. To calculate the standard deviation, okay, so our P sub naught equals 0.5, okay, up here, so we just put that in here, times 1 minus that P sub naught, which is 0.5, okay, and then you divide that whole thing by n. Remember, your n are the number of observations, and you had 500. And so that is our calculation of standard deviation. And if we calculate the z statistic, okay, by putting this standard deviation calculation down here, and then we look at the population parameter here, minus our certain value, okay, or value of interest here, so 0.556 minus 0.5 over our standard deviation, we calculate our z-score or z-statistic as 2.504. Okay, so what? Now we have this value, the z-statistic is 2.504. We now have to look at what that means and how we decide to reject or fail to reject the null hypothesis. So there are two methods of making a statistical decision regarding a null hypothesis. One is the rejection region approach, and the second is the p-value or probability value approach. Of the two methods, The latter is more commonly used and provided in published literature. So when you read primary literature, when they discuss the statistics that they ran and their results, they will give a p-value for the data, and that helps them interpret or make a decision based on the data. So even though this is the more common and is used and provided in published literature, however, understanding the rejection region approach can go a long way in one's understanding of the p-value approach itself. Regardless of method applied, the conclusions from the two approaches are exactly the same. In explaining these processes in this section of the lesson, we will build upon the prior steps already discussed, i.e., or in other words, setting up hypotheses, stating the level of significance as alpha, and calculating the appropriate test statistic. So, continuing with our one proportion example of in-state UAB students. Say we take a random sample of 500 again, same data, and we get 278 are from Alabama. Can we conclude that the proportion is larger than 0.5 at a 5% level of significance? If we use the rejection region approach, step 1 asks, can we use the one proportion z-test? Okay, so we have to check those assumptions first of all. So step 1 is to check whether or not n times p sub naught, or 500 is your n, p sub naught is your certain value, 0.5, that equals 250, which needs to be greater than or equal to 5, and it is. The other assumption or condition that has to be met, n times 1 minus p sub naught, 500 times 1 minus 0.5, again gives you 250, which is greater than or equal to 5. So your assumptions have been met. So since the hypothesized value of p sub naught is 0.5, we can check these assumptions. Step 2 is to decide significance value, or alpha. According to the question that was given, that I read to you, alpha is 0.05 because the question asked, can we conclude that the proportion is larger than 0.5 at a 5% level of significance? So from the question that was asked, we know that alpha is set at 0.05. The next step, or third step, is to calculate or compute the value of the test statistic. This was as we previously did in calculating the z statistic, which we utilized this equation here to calculate our z statistic of 2.504. Step 4 is then to find the appropriate critical values for the test using the z table. Write down clearly the rejection region of the problem. We can use the standard normal table, or we can use the last row of our t-table, okay, this is the t-table, to find the value of our z statistic at 0.05. Since the last row for degrees of freedom on our table is infinite, and this refers to the z value. Okay, so let me explain this just a little bit more. So what you have here is just a picture of what the z-table looks like. So in Canvas, the z-table is uploaded, so you should go and open that t-table. So take a minute to do that. Once you have pulled up the t-table, you will see that along the top here you have your t-values with the alpha, okay, and as a sub numeral here, and we are looking for a one-tailed test, okay, right? It's a right-tailed test here. We've already defined this as a one-tailed test. So you're looking at this column here, and your significance level is 0.05, okay, so the confidence interval then here is 95%, right? And so this is the row you're looking for, and if you look down here, these are the degrees of freedom, so 1, 2, 3, 4, okay, and then obviously this table is cut off. And so I'm going to take a minute to pull up the actual PDF version of the t-table for which you have And I will show you how to find the z-value so that you can find the critical value for this test. Okay, so here is the t-table. Okay, it's a PDF. This is what I was showing you. It was cut off. I just showed you the top part up here. So here's your one tail line here, and you're looking at 0.05. So this is the column that we're interested in looking at here. Maybe I can highlight that so that it will be obvious. If you scroll all the way down to the bottom, to the very last row here, you see Z listed. This is degrees of freedom as infinite, which is also known as the Z. And so the confidence level we're looking at here, it's this column here, okay, 0.05 for a one tail. If it was a two tail, it would be 0.10, okay, so same column. Come all the way down, look over the Z, and our critical value is 1.645, and that's all you have to do. So now we know the critical value, okay, and here you can see the whole table. So the critical value for our test at significance of 0.05 is 1.645. So from the table, we were able to find the Z at 0.05. It's found to be 1.645, and thus the critical value is 1.645. The rejection region for the right-tailed test is given by Z of 1.645, which looks like this, so the bright yellow right-tailed region here. The fifth step is to check whether the value of the test statistics falls in the rejection region. If it does, then reject the null hypothesis and conclude the alternative hypothesis. If it does not fall in the rejection region, do not reject the null hypothesis. So the question is, does the value of the test statistic, which was 2.504, fall in the rejection region? The rejection for the right-tailed test is Z is greater than 1.645. So the observed Z value at 2.504, okay, that's our test statistic. So since Z falls within the rejection region, we reject the null hypothesis. Our last step is to state the conclusion in words. With a test statistic of 2.504 and a critical value of 1.645 at a 5% level of significance, we have enough statistical evidence to reject the null hypothesis. And in so doing, we conclude that a majority of the students are from Alabama. So for using the p-value approach as opposed to the rejection region approach we just talked about, if we keep with the same question, are the majority of students at UAB from the state of Alabama, we already know, okay, that here is your population parameter value, your certain value of 0.5. Your null hypothesis is that that parameter is equal to 0.5. Your alternative hypothesis is a right-tailed hypothesis. It asks us whether or not, because the question has to do with majority, if that population parameter is greater than 0.5. And again, remember, this is what a right-tailed test looks like. And this is going to become important for using the p-value approach of knowing what these normal distributions look like and where our alternative hypotheses fall. And in this case, it's here on the right side. So for the p-value approach, steps 1 through 3 are the same as the rejection region approach. So in the first step, you check the conditions, which we did here, the conditions that have to be met for a one proportion test statistic. Step 2 is to set the significance level. In this case, it was given in the question at 5% significance, so alpha equals 0.05. In the third step, we calculated the Z statistic using this equation here, and our Z statistic was calculated as 2.504. So the next step, or step 4, this is where the differences start. We need to compute the appropriate p-value based on our alternative hypothesis. So this is our alternative hypothesis, right? So P, our parameter proportion, is greater than 0.5, which is a right-tailed test. So what does that mean? What are we talking about? So in this step 4, when we compute the appropriate p-values, these are the 3 ways in which this falls out. If the alternative hypothesis is right-tailed, then the p-value is the probability the sample data produces a value equal to or greater than the observed test statistic. And the calculation for one proportion right-tailed p-value approach looks like this here. For a t-test for means, it looks like this. Okay. If the alternative hypothesis is left-tailed, then the p-value is the probability the sample data produces a value equal to or less than the observed test statistic, which looks like this here, or this for a test of means, or a one mean test. If the alternative hypothesis is two-tailed, then the p-value is 2 times the probability the sample data produces a value equal to or greater than the absolute value, denoted by the absolute value bars here, of the observed test statistic. And remember, this is important. It's 2 times because it's two-tailed. Remember, you have both sides of your normal distribution highlighted in whatever color. Okay, so remember that. So for this question, if we go back just a second, here's our alternative hypothesis. Our population parameter or proportion is greater than 0.5, which is a right-tailed test. So that puts us right here in a right-tailed analysis. So the p-value is the probability the sample data produces a value equal to or greater than the observed test statistic. And this is what our equation is going to look like here. So p times z greater than our test statistic or z statistic here. So if we calculate this out, so you have your p-value is equal to p of your z greater than your z statistic. And so we've already calculated our z statistic. Remember, here, this is how we calculated it before when we looked at the region of rejection or rejection region approach. Using this, we can calculate what the p-value is, and we know that our z statistic is 2.504 based on this calculation here. So we can use that value to get our p-value, which is 0.0062. So no, that's not magic of how I got to that number. So hopefully you noticed in Canvas when you pulled up your t table that there was also a z table. And so we need to know the value of the z so we can calculate the p-value. And in order to do this, we're going to look at that z table, which is also called the standard normal probabilities table. And when you pull that up, you'll notice at the top of the pages, you'll see a normal distribution here, and you'll see your z here. The table entries, so the entries in the table, all the numbers that are below this, represent the area under the standard normal curve to the left of z. So this shaded region here. And I'm pausing for a second for effect that if this is what the standard normal probabilities are for this region here to the left of z, and I'm just going to go back 2 slides here to show you this is our alternative hypothesis here, which tells us that our population parameter or portion is greater than 0.5, which gives us a right-tailed test. And if we look at that, what it looks like here is this is the area that we're looking for, right? And so if our z table is giving us this here, we're interested in knowing what's right of that z. Okay, so what we're going to do is I'm going to take us to what the z table looks like. So here we are. Here's our z table. Here's this top part that we were just looking at. Okay, it tells you that this is page 2. So on page 1, this is the negative values. Okay, so you're looking at z to the left of z here. If you scroll down to the positive numbers, okay, of your z here, so our z statistic was calculated at 2.504. This only goes out to 2 decimal places here. What this table is showing is all these values here on the table represent the probability value for this area under the curve here that's left of the z value. The z value, okay, which is shown here on this column and this column, is how you figure out which one of these probabilities fits into your gray area, okay, or the left of z. So our z statistic was 2.504. So we are going to go down this column here, down the rows until we find 2.5. So let me get the highlighter. So 2.5, it was 2.504, so there's not one of those. This wouldn't be it because this would be 2.54. Okay, that 4 would be the digit right after the 5. And so what we're going to do is just use the value for 2.50. And so that gives us this number right here, 0.9938. So that's our probability, okay, for this shaded area that's left of our z value. So that's the value that represents this here. That was 0.9938. Okay, and the way that we calculate our p-value of interest for the area to the right, okay, this area here, or also known this area here, okay, our z was 2.504, so everything to the left of that falls into this category, 0.9938. This entire line represents a value of 1, and so 1 minus that value we got from the z table, or the standard normal probabilities table, 0.9938, equals 0.0062. So our p-value is equal to 0.0062. So since the p-value is equal to 0.0062, and that value is less than 0.05, which was our alpha value, we reject the null hypothesis. So that is step 5. Step 6 is writing a conclusion or statement in words. And we can state that with a test statistic of 2.504 and a p-value of 0.0062, we reject the null hypothesis at a 5% level of significance. We can conclude then that a majority of the students are from Alabama. As you can see, both approaches, the rejection region approach as well as the p-value approach, ensure the same conclusion, and either approach will work. However, using the p-value approach has the following advantages. 1, when you use the rejection region approach, you need to check the table for the critical value every time people give you a different alpha value. The second advantage to the p-value approach is that in addition to just using it to reject or not reject the null hypothesis by comparing p-values to your alpha value, your p-value also gives us some idea of the strength of the evidence against the null hypothesis. So as a review, there are 6 steps to conducting a statistical test. The first step, coming up with your null and alternative hypotheses, or you're devising your competing hypotheses. You then select a level of significance, or alpha, which is generally 0.05, but can also be 0.1 or 0.01. You decide what test statistic you're going to use. In the examples that we talked about today, we utilized the 1 proportion test. You can also utilize, so that was looking at proportions, and you can also utilize the t-test method for comparing or looking at 1 mean. We'll talk about more types of test statistics after we come back from spring break. You need to compute the p-value if you're doing the p-value approach, and check whether to reject the null hypothesis by comparing your p-value to alpha. And then your final step is to come up with a conclusion in words. A reminder, of what a p-value in hypothesis testing is. P-value is a probability of obtaining a value of the test statistic or a more extreme value of the test statistic, assuming that the null hypothesis is true. A word of caution. Sometimes p-value is also referred to as the level of significance. One should be aware that alpha is also called the level of significance. This makes for a confusion in terminology. Alpha is the preset level of significance, whereas p-value is the observed level of significance. The p-value, in fact, is a summary statistic which translates the observed test statistic's value to a probability which is easy to interpret. Our next lecture will focus on two-sample test statistics, and we'll start with t-tests where we compare two different means.